The next speaker of today is Silvia Sciutto. She's a PhD student at the University of Genoa. And today she will talk about continuous injective generative neural network.
Yeah, thank you. And thanks to the organizer to give me this opportunity. I work at the University of Genoa, as he said. And my supervisors are Matteo Santacesare and Giovanni Alberti. And this work is not published yet. So it's the first time we present this work, and it's my first presentation too. These generative neural networks are used, in our case, to solve inverse problems. In my case, I use this generative neural network to solve the electrical tomography inverse problems that I will explain you later. Non va il puntatore.
Sì. Perché è qua.
Ah, ok. So, I can see I can see the outline. I read from the computer. The first part is a general introduction in generative neural network and in variational autoencoder. And then I move to generative neural network in the continuous layer. That is our work. We try to extend the concept of generative neural network to the continuous world. And then I will study generator injectivity that allows us to guarantee stability in our inverse problems. And then I will show you a possible application, that is the electrical impedance tomography. So this is a first introduction to generative model. A generator or a generative model try to generate images as similar as possible to those of the training set. In this case, for example, the training set is composed by real people, and this generator try to reconstruct images that are fake people, that are almost indistinguishable from real people. And we use this structure, in particular a structure like this one here, where we start with a little vector z that belongs to a simple and known distribution. In this case, z belongs to a normal distribution. And then we project and reshape, and we do some convolutional layers in order to obtain an image as output. The first layer is a fully connected layer, as we will see later. And the others layer are convolutional layers. And this is a structure we use in our work, and is a very common structure. As we can see, the convolutional layer presents the same structure, in the sense that we start from a number of images of size 4 by 4 in this case, and we at each lever decreases the number of images, but we increase the size of the images. So the structure is like this. And the first layer, as I said before, is a fully connected layer. That means that it is composed by a linear matrix F, that in the continuous case will be a linear map, a bias term B, and a nonlinearity sigma, that is a pointwise nonlinearity, that is applied to this whole fully connected layer. This layer is called fully connected because each input neuron is connected to each output neuron through this matrix F. And this is, as I said before, the first generator layer. The other layer are fully connected layer, and they have this form here. We have CE input channel that are the input images as before. We have CO output channels, and we use the filters that depends both on the input channel, that is this I, and on the output channel, that is this K. We have biases BK, and we introduce a new variable that is this stride S and the nonlinearity. And we can see that the K output image is sigma applied to the sum over the input image of the convolution between the input image and the filter plus the bias for every K in the output channels. We have to define what is this convolution with stride S. And this convolution is written here, where we can see that the term S appears as a variable of the filter T. In this case, F is the input image, T is the filter, and F convolved with stride S with T is the output. And what is the stride? The stride is, as we can see here, for example, or here, the number of pixels by which the filter moves into the image F. In this case, the filters are red, green, and blue. The output image is this one, the input image, sorry, and the output image is this one here. And as we can see, if the stride is, for example, 2, the filter moves along the image by 2 pixels in 2 pixels, and so the output size is influenced by the stride. So in this case, the output size is half of the input size. If, for example, the stride is 3, the output size is 1/3 the size of the input size. But this is not our case, in the sense that I say you before, that in the generator, the output size is bigger than the size of the input. And so this means that our stride S is strictly less than 1. And we don't know how to modelize this concept in terms of pixel moving, as I said, for stride 2, for stride 1, or for stride 3, for example. So these are the convolutional layers, and this is the structure I use to solve the inverse problems. That is quite similar, but it involves 2 different maps: the encoder map and the decoder map. The decoder, in this case, plays the role of the generator. In fact, we can see that we take in input a little vector, and we obtain in output an image, as the generator that I told you before. While the encoder do the opposite thing, takes an image and compress the image into a little vector. This space here is called low-dimensional latent space, and it is low-dimensional because we chose this eta here very small, because we want first to compress an image and then to expand the image in order to obtain a replica image that is as similar as possible to the original one. So the variational autoencoder goal is that this original image X is as similar as possible to the generator, that is the decoder, of the encoder of the original image X. This G of I of X is the replica image. We apply this structure to inverse problems. But first, I want you to introduce to a classical approach to inverse problems. An inverse problem is a problem like this one, where our operator is f, our unknown, so what we want to reconstruct, is x, and our measurement is y. And in some sense, we want to invert this operator f in order to obtain our unknown x. A first iterative approach, this is only an image that represents a brain, and through the operator f, we can see the y, the measurement y. And so it is simple to go from this x to this y. But it's not simple the reverse, so going from this measurement to the image of the brain. But this is not my application, just an image to show you what an inverse problem can be. Our approach is this one. We have two steps. In the first step, we train a variational autoencoder, that is a structure that I said you before, on a training set x1, xn of possible solution. So this means to give on the unknown x a sort of prior distribution. Because, for example, if we know that our solution x is a function with some properties, we show the training set x1, xn as a function with similar property of our x. And then we solve the problem, but we don't solve the problem y equal to f of x. We solve the problem introducing the generator part, that is the decoder of our variational autoencoder. So we solve the problem in a little space, because we solve the problem in the variable z and not in the variable x, where z is in this space, so it's very small. The advantage of solving this problem in this way is a computational advantages, because x belongs to a very large space, while z belongs to a very little space. And moreover, there is the idempoteness reduction of the inverse problem, y equal to f of x. So z is sampled in a simple distribution, and then applying the generator we find x in some sense, that it is what we want to recover, and applying the f that is our operator, we find the y, the measurement. Now I move to our continuous generative neural network. And first I want you to introduce some concept of wavelet analysis. We use in our work the wavelet analysis because we are interested in analyze a signal in its frequency time domain. And to do this, we use functions that are these psi that depends on two parameters, B and A and B, where A is a dilation parameter and B is a translation parameter. So changing A, the oscillation, the velocity of the oscillation of psi change. While changing B, we translate the wavelet psi along the time domain. And we don't use continuous wavelet where A and B belongs to R, but we use discrete wavelet where there are two different parameters that are J, the scale, that plays the role of the dilation A, and K, the translation. I write K and not P because K is a different parameter from B, because this translation parameter in the discrete wavelet depends on the scale. So, in the sense that bigger is finer is the scale, and smaller is the translation parameter. Finer is the scale means that the psi oscillates fast. And if we have a function that oscillates fast, we have to translate it of small step. As I said before, this analysis is useful to analyze the frequencies of a signal. Related to the function psi as before, we have this function here, phi, that I don't want to introduce, but this phi is related to the psi as before, that is called scaling function. And the spaces generated by the scaling function, varying the translation parameter k, are the space that contains all the function with scale 2 to the minus j plus 1 and coarser. So we can see that from this definition here, that each space is contained in the following space. That means that Vj is contained in Vj plus 1, because Vj plus 1 contains function with finer scales with respect to Vj. The dimension shows in k from 0 to a certain number that I don't want to say you to explain, is 2 to the power of j. And if we take the closure of the union of the Vj, we obtain the space L2 of 0, 1. These spaces are very important because we use these spaces in our continuous formulation. Why we use these spaces? Because the generator increases the size of the image. And this is like passing from a space with coarse scales to a space with finer scales, because we represent the image with more pixels. And this is an example of taking a signal f. We can decompose the signal by projecting this signal on to the spaces, the scaling spaces. As we can see, if we increase the scale j, the space become coarser. So we analyze the coarser scale here, and here the scale is fine, is very refined. Then I want to recall you the structure in the discrete analysis. The generator has first a fully connected layer that is composed by this matrix F and the bias. Then we have the nonlinearity, that is a pointwise nonlinearity, so it acts component-wise. And then we have all the convolutional layers, where, as I said before, the number of channels, so the number of images in this case increases. Sorry, the number of images decreases. In fact, this C1 is less than this C2, while the length of this vector, because I talk in 1D. So first, before I talk about the number of pixels. Now I'm moving in 1D for simplicity, but it's simple to extend this structure in 2D. And so I talk in terms of vector length. The vector length increases as the number of pixels as before. And then we have all the convolutional layer. In order to obtain only one channel that where this alpha L represents the desired signal size, and capital L is the number of the layer. As I said before, the number of channels decreases until one channel, while the length of the vector increases until having the desired vector size. And this is the image I showed you before. In the continuous case, the idea is quite the same, in the sense that we relate the length of the vector with the scale j of our scaling spaces. More the vector is more the length of the vector. One moment. If the vector is very large, the vector belongs to a very fine space, a very refined space. While if the vector is small, the vector belongs to a coarse space. And this is the structure replacing R to the power of alpha with our scaling spaces Vj. But this is the same structure as before, where the scale decreases until JL. And in this image, we can see the philosophy beyond the generator, that is passing from coarser scale to finer scale. So at each level, at each layer, we pass from a coarse representation to a more fine representation, until having a very fine image or vector in this case. But there is a problem that we don't know if after the nonlinearity or after the convolution we remain in a scaling space. So to do this formally, we have to introduce projection. This projection here, projection after each nonlinearity and after each convolutional layer. And this is the real formalization we give about our convolutional generator or convolutional generative model. I want to make an observation. The filters of the convolution has to belong to the refined space, in the sense that if we have an input that belongs to a low resolutional space, we have to choose the filter in the refined space in order to obtain the output in the refined space. So for each convolution phi L, the filters T belongs to VJL, that is the refined space. Now we study generator injectivity, that is written here, but you can see this. We study generator injectivity, as I said before, to obtain Lipschitz stability of our algorithm. The algorithm that I show you at the beginning with two steps, the training step and the iterative step. This is our main result. We fix for simplicity the stride equal to 1 to 2 to the power of nu. As I said before, the stride is less than 1 because this nu is positive. We take the structure of the generator that I showed you before, but without the convolution, the projection after the nonlinearity. If you remember, there were a projection after each nonlinearity. But in this theorem, we remove this projection And we can do this because we choose as scaling spaces, they are scaling spaces that are particular spaces of a particular wavelet function. That is the R function. It's a very simple function. And with these 4 conditions, we obtain the injectivity of the whole generator G. The first condition is a condition on a fully connected layer, and we ensure that the fully connected layer is injective. Then we impose that this sigma is injective, and these 3 and 4 conditions are the real difficult condition, because we have to find some condition on the filters to have the injectivity of the convolution followed by the projection. As we know, the projection can cause trouble for the injectivity, but we impose condition so that the convolution composed with the projection is injective for each layer. These conditions are shown in the next slides, and this 4 condition is a technical condition that I don't want to explain. That this 3rd condition is the very important condition of the theorem, and is a sort of independence between the filters component of each layer. So, as I said before, the filter Tik can be decomposed in this way because they belong to the space Vj. In this case, I restrict the maps to the first fully connected layer, but this structure is the same for the next fully connected layer. But we analyze the first one. So you can decompose the filter in these components because Vj2 is generated by this function here, and the condition on the filters is a condition on this coefficient d, p, ki, where k and I are output and input channel, while p is the translation parameter. And the condition we find is that the composition of these 2 maps is injective if and only if the determinant of D is different from 0. That is a very simple distribution. There are some calculus beyond these formula, these results, but I skip it, and I just give you the result. That is that we have to impose that the determinant of D is different from 0, where D is a matrix that depends easily by this coefficient D, P, K, I. And so it's easily to compute this determinant. And as I say you before, this condition of determinant of D is different from 0 is the same that imposing linear independence on these vectors, varying P and K. So, now I show you a possible application that is the electrical interferometry. I'm sorry, but black, you don't see the outline of the talk. Our possible application is the electrical impedance tomography, also known as Calderon problem. And this problem is composed by a partial differential equation, that is this one here, and a boundary data. We choose Neumann boundary data, where the operator f of the inverse problem is this Neumann to Dirichlet map computed in gamma. and we want to recover gamma. So we have this map, that is our measurement y, and we want to recover our unknown gamma, where the map is this one here. We have the boundary data, and we find the solution with that boundary data and this gamma. As I said, the forward problem is to find the Neumann to Dirichlet map from gamma. And so what we have to do, we have to solve this equation here for every boundary data G. But in practice, we are not interested in this problem, and if we have to solve an equation like this, we have the boundary data G. So we don't want to do this computation for every boundary data G. While the inverse problem is from the Neumann to Dirichlet map, we want to find, computed at gamma, we want to find gamma. In fact, we have not the whole map, the whole Neumann to Dirichlet map, but we have only a discretization of this map, because we can't know the map for every G. We have a finite number of these boundary data G, and we know only a discretization of this Neumann to Dirichlet map. In practice, we have this structure. The G plays the role of the current I, that is that pass belong these electrodes from 1 to 16. The solution U, G, gamma is the voltage V, and we can measure the voltage in order to recover from these two quantities. We recover the Neumann to Dirichlet map, and once we recover the Neumann to Dirichlet map, we want to find gamma, that is the conductivity. So we want to find the values of the conductivity in the whole domain omega. In this case, the values of the conductivity are only 2, because we have 3 inclusions with the same conductivity value, and the background has a conductivity value that is different from the inclusion. As I said before, what we do is, given a training set of conductivities, of possible conductivities, the variational autoencoder learn how to compress and then to expand and generate new conductivities. And then there is the iterative part that consists in applying a Landweber type algorithm, that is an iterative algorithm, to the low dimensional space, that is the space Z, that is the compressed space, the space of compressed conductivities. And in this case, with our structure, we find that this algorithm is Lipschitz stable thanks to the generator injectivity. So we construct first our generator, then we study the injectivity F, and if we impose the condition of the theorem that I showed you before, we obtain Lipschitz stability. And this is a very preliminary result, just to test our algorithm in a simple case. We have an initial guess, that is our conductivity, that is constantly equal to the value of the conductivity at the background. And we want to reconstruct this inclusion here, where the training set in this case is composed by in our training set, the inclusion moves in the image at and can be of different colors. That means that can assume different values. And we want to reconstruct this image. And we obtain this result that is not pretty, but it's a very preliminary result. And I also have to observe that in the EIT inverse problems, the images are very blurred. So it's normal to obtain a blurred image. And also in this case, I chose a very little low dimensional latent space, because the low dimensional latent space has dimension 10, while the image has dimension 128 times 128. So it's very difficult to approximate this real solution in this case. Now I want to tell you some future extension. We want to extend our injectivity theorem to other wavelets, because I analyze only the R wavelet. We want to study the injectivity for more general continuous generative neural network, because I consider only one kind of generative neural network. And I want to extend the result also for a generic stride, because I consider the stride 1 to 2 to the power of nu in my theorem. And from the practical point of view, I want to generalize the training set of the electrical impedance tomography problem, considering more than one inclusion or medical images. And I want to apply this algorithm to other inverse problems in general. Thanks for the attention. This is a trash image, but I like it, so I put it on the last slide.
Okay, thank you, Silvia, for your presentation. So is there any question?
So I have two questions.
Okay.
The first one is that slide, I think, 8. It is about the equivalence reduction. So can you comment on the equivalence reduction?
Yes. This is really I cannot comment this line, because my supervisor tell me to add these things without telling me why these things is true. But I only study the computational advantages of this formulation in practice. I don't study the impedance reduction.
But what is, the size of y? For example, in your example.
Okay. Yeah. We consider, for example, 6. We consider here 16 boundary data, and so we have a discretization of 16 Neumann, 16 values of the Neumann to Dirichlet map, and then we project each solution, because we have to do another discretization, and we project this solution on other 16 functions as basis, and so we have y as is 16 times 16 in our case. Okay. Because a discretization of the Neumann to Dirichlet map.
And another thing, I didn't understand the Weber here?
Here. So I do the Langweber iteration on the space of Z. So at each time my problem involves both the derivative of the forward operator, that is the Neumann to Dirichlet map, and composed by the derivative of the generator, because we try to apply the Langweber algorithm to this problem. So at each time we apply a composition of, we apply the iterative algorithm to this composition. And so we both have to compute the gradient of F and the gradient of G, the generator.
Okay, thanks.
Okay, is there any other question?
Yes. Have you tried with a bigger eta? For example, you tried with
Yes.
eta equal 10, maybe 100?
Yes, I don't try with the very large eta, because the computational cost would be very high, and we want to reduce the computational cost. So I tried with the eta until 50,
Okay.
but not
And
more.
There are some differences in the solution obtained with eta, a bigger eta instead of that one, or?
Yes, there are differences, but not so much difference, because the training set is very simple. If we think the training set is only a circle, so it can be represented by 3 dimensions that are three. That are the ray and the 2 coordinates of the center, and the color that change. So we can think that we can choose eta 4, because this image has 4 parameters. And so I think that 10 is a sufficient number.
And are you interested only in the fact that there are 2 different regions and you want to find the region, or in the Calderon problem you would also like to know the value of the conductivity?
No, I want also to recover the value of the conductivity, but the value here is represented by the color. There are darker ball, and there are also white ball that represent lower value of the conductivity with respect to the background value, that in this case is 1.
And for what concerns here the reconstruction, the value that you obtained is similar to the real one?
Yes, are quite similar, but the position, as we can see, is not so similar. But we do only 29 iterations.
Okay, thank you.
Okay, is there any other questions? Okay, so I have one. Actually, he just asked my question, but I have another one. I missed something when you introduced the R space.
Yes. I don't introduce the formula of the R wavelet.
Okay, doesn't matter. But why did you do that? Why did you use the R space?
Yeah, I
Because
use
of
the
the
R
nonlinearity?
space to simplify the generator structure, because without using the R space, there will be a projection after the nonlinearity, because we are not sure that this nonlinearity give us function in the Vj space. While using the R space and applying the nonlinearity, we are sure that starting from Vj, we remain in Vj.
Okay, sure.
And so it's a simplification, but we want to extend to other wavelets.
Okay, but so this works with every nonlinearity, or just the one you used?
No, it works with the nonlinearity that are defined pointwise. But they are the nonlinearity that we always use in neural network.
Okay.
So, for example, if we want to go from Rn to Rn with sigma, in fact we apply sigma to each component.
Each entry of the vector. Okay.
Yes.
Okay.
They are used, it's almost the only nonlinearity used are pointwise nonlinearities.
Okay. Okay, so with the hard space, you're sure that you don't fall out of the space?
Yes.
Okay. Okay.
We prove it, but I skip the proof.
Okay. So if there are no more questions, I thank again Silvia.